I've got a problem up here on the board. We want to find the location and value of the constrained max and min for this function f. It's a linear function of 3 variables. So f of x, y, z is 2x plus 3y minus z. And our constraint is given by this equation. And I just want to emphasize that it's given by an equation, not an inequality. So I've got x squared plus z squared plus y squared plus z squared equals 9. I know that's just the surface of the sphere of radius 3. I can view that as a level surface of this function g of x, y, z. And unlike some of our previous problems, I'm not working with that surface and its interior. I'm just working with that surface. When my region is defined by an equation, that just gives me a level surface in this case. If I had a function of 2 variables, it would be a level curve. I do not need to check critical points for f separately. All my points are on the boundary. Any place that's a location of a max or min will be a solution to the system of equations that I set up. Because remember, that system of equations comes from the gradient of f equaling lambda times the gradient of g, together with this constraint being satisfied. If lambda is 0, I'm at a critical point. So if there are any critical points that happen to be on this sphere, we will get them as solutions to our system of equations. The time I have to check critical points as a separate step is when I'm working with a region that includes both points that are on the level surface that's defined by my constraint equation and other points that are on one side of that boundary surface or the other. What we've seen before is a sphere and its interior. Then I would have to check critical points as well. Here, I don't, which is kind of nice. Okay, so let's just use the method of Lagrange multipliers. Oh, before we do that, I think I will just mention, I said to find the location and value of the constrained max and min. How do I know they exist? That's continuous. That's a sphere of radius 3. It's closed and bounded. Okay, so the extreme value theorem ensures, in this case, that an absolute max and an absolute min do exist. Okay, so the gradient of f is just going to be 2, 3, negative 1. Notice since f was a linear function, the gradient is constant. Now for this problem, we've just said we don't need to check critical points, but if we did, that would be a really quick check because this gradient is always defined and never 0. So it doesn't actually have any critical points. All right, let's take a look at the gradient of g. That's going to be 2x, 2y, 2z. And while that is 0 at the origin, it's certainly not 0 at any point on the surface of that sphere. So this is not equal to 0 on our constraint surface. All right, so I'm looking for places where the gradient of f is lambda times the gradient of g. Let me just write that out in terms of the components of my vectors, and then we'll get our system of equations. Okay, so the gradient of f we said was 2, 3, negative 1, and that's got to equal lambda times this. I'm just going to do the scalar multiplication, so I'm going to insert a lambda in each component. So that would be lambda times 2x, lambda times 2y, lambda times 2z. And if I want to create a system of equations, my first equation will simply tell me that my first components have to be equal. So 2 has to equal lambda times 2x. My second equation will tell me that my second components need to be equal. So 3 will equal lambda times 2y. My third equation will tell me that my third components need to be equal. So negative 1 will equal lambda times 2z. And then my fourth equation is the constraint equation, x squared plus y squared plus z squared is equal to 9. Excellent. Now, my general approach here is that a lambda shows up in those first three equations. If I can solve for lambda, I can then say this lambda is the same as that lambda is the same as this third lambda. That'll give me a relationship between x, y, and z that I can then plug into the constraint. Now, usually I start by saying, well, what could go wrong? If I want to solve for lambda, here that would involve dividing by 2x. And as a general rule, I can't divide by x unless I know it's not 0. I know it's not 0. Because lambda times 2x is 2. If x were 0, this product couldn't possibly be 2. It's very nice when lambda multiplies by something to give me a number other than 0, because then I know all of the factors on this right-hand side are not 0. By a similar argument, I can see that y is not 0, because then this product couldn't be 3. And z is not 0, because otherwise this product wouldn't be negative 1. So I'm just going to make a note here. X, y, and z are not 0. If you know that variables are not 0 and you're going to divide by them, just do tell me that you know that, because very often students divide by variables when they don't know that they're not 0. And so if you just start dividing, I'm going to be concerned. If you tell me why it's okay, that you know that they're not 0, and here I could even say, because otherwise 1, 2, or 3 leads to a contradiction. Excellent. So this is a really nice problem. Not only did we not have to check critical points separately, we don't have cases because nothing can go wrong. I almost feel superstitious, like I shouldn't have said that. Okay, let's see. From equation 1, if I solve for lambda, I'm going to get that lambda is equal to 2 over 2x. And of course I can cancel those 2's, so lambda is 1 over x. Using equation 2 to solve for lambda, I'm going to get that lambda is 3 over 2y. And using equation 3 to solve for lambda, I'm going to get that lambda is negative 1 over 2z. Now, using the brilliant observation that lambda is the same thing as lambda, which is the same thing as lambda, I can say that 1 over x is equal to 3 over 2y is equal to negative 1 over 2z. And I don't want to work with all of that information at once, but let's just pair them off. If 1 over x is 3 over 2y, I can cross multiply. 2y equals 3x. That's a 2y equals 3x. Y is 3x over 2. Could have solved for x or for y. I chose to solve for y. Okay. Now, I want to get some z's in there. So let's see. Since I got y's in terms of x's, I think I'll just work with these two. Negative 1 over 2z is equal to 1 over x. So negative x is equal to 2z. Z is equal to negative x over 2. Y was equal to 3x over 2. Go ahead and write that down. And of course that implicitly uses this relationship. This gives me a relationship between y and z. But if they both have that relationship to x, I can figure out the relationship between y and z as well. All right, so now I can use equation 4. I've expressed everything in terms of x, so I'm going to just plug in. I'll have an equation in just x, and I'll solve for x. So x squared plus y squared becomes 3x over 2, the quantity squared, and z squared becomes negative x over 2, the quantity squared, and that equals 9. So x squared plus 9x squared over 4 plus x squared over 4 is equal to 9. That's 10 fourths, or 5 halves, x squared x squared would be another 2 halves of an x squared. So that's 7 halves x squared is equal to 9. And now, by the magic of video editing, my board has changed just a little bit. That's generally a sign that I made a careless computational error in the first take of the video and didn't want to redo the entire problem. Not that that ever happens. Okay, so we had 7 halves x squared equals 9. That means x squared is going to be equal to 18 over 7. So x will be plus or minus the square root of 18 over 7. I'm going to go ahead and simplify that a little bit, although I would consider this simplification optional because these problems are so long. So that's plus or minus 3 root 2 over root 7. And if I want, that's plus or minus 3 root 14 over 7. Okay, excellent. So I have two possibilities for x. Notice, though, once I know x, y is 3 halves of that. If y is a positive multiple of x, x and y must have the same sign. So when x is positive, so is y. When x is negative, so is y. So sometimes we're mixing and matching signs. Here we're not. Z is a negative multiple of x, so it's always going to have the opposite sign of x. So that tells me that I actually just have 2 points. X, y, z, and then, f of x, y, z. So if x is positive 3 root 2 over 7, then y was 3 halves of that. So that would be 9 root 2 over 14, and z was negative 1/2 of that. So that's going to be negative 3 root 2 over 14. And then if x is negative 3 root 2 over 7, y is negative 9 root 2 over 14, and z is negative 3 root 2 over 14. Excellent. So now let's evaluate f. It's been a while, but f was 2x plus 3y minus z. So what I'm going to do is I'm going to first of all just get a common denominator. I can rewrite this as 6 over 14 times root 2. So 2x is 2 times 6 root 2 over 14, plus 3y will be 3 times 9 root 2 over 14, minus z will be plus 3 root 2 over 14. Okay. So it's all going to be over 14. Okay. And I've got some root 2's. So here I've got 12 root 2 plus 27 root 2 plus 3 root 2 all over 14. Let's see, that's 42 root 2 over 14. And I can just reduce that. That's going to be 21 root 2 over 7. Now, with my second point, x, y, and z are just the exact opposite signs. That's just going to change the sign of each of these terms. So I'm going to get exactly the opposite result, negative 21 root 2 over 7. So pretty clearly, the positive one is going to be my max, and the negative one is going to be my min. So f has a max of 21 root 2 over 7. It occurs at point A. So I should probably give this point a name and call it A. I just don't feel like writing those fractions again. Let's call the other point B, and we can say f has a min of negative 21 root 2 over 7, and it occurs at B. Excellent.